Thank you, Mr. Youssef, for that enlightening speech. Moving forward, now I would like to invite on stage Professor Omar Yaghi, James and Nelche Chair, Professor of Chemistry at the University of California. He invented a new field of chemistry, reticular chemistry. Please put your hands together for Professor Omar.
Thank you very much for making the introduction brief, and I'm delighted to be here. Your Excellencies, ladies and gentlemen, I want to share with you our research that I think is leading to what I call the air economy. There's plenty of air. If we can take CO2 from air and then turn it into fuel, then we would have cleaned the air. And then if we can take water from the air, especially from desert air, then we would have created drinking water and water that could be used for agriculture in areas of the world that are water stressed. Furthermore, if I can trap water from desert air, then I can trap water anywhere in the world at any time of the year. So all problems are related to materials. And what I want to share with you today is how far we have gotten along this in realizing this vision. So I think that many of us are familiar with this problem. This panel here is in the year 2000. This is Lake Mead. It's a reservoir on the border of the Arizona-Nevada. And you see this body of water is being depleted. This is 2000, 2021, 2022. Okay? That tells you the severity of the situation, and it's not just in the western of the US, but it's also a problem that is also realized in the Rhine and the Yangtze River, major rivers in where large populations rely on the water. So it's a problem, and it will get worse. For the first time, I think, in a long time, by the way, we humans never do anything about a problem until it hits us in the face, until it really gets to our front door, affecting our family and our livelihood. And this is now has come home in the sense that climate change is no longer a problem. It's affecting our day-to-day life and our livelihood. The red lines that you see here indicate the severity of these weather events, land heat waves, ocean heat waves, wildfires. They're all getting more and more severe. And we feel that in California, where I live, we feel that every season. So the weather events are getting more severe. Diseases are transmitted much more likely in dry areas of the world, and air quality gets poorer, as well as food security is lessened, and the water stress even gets worse. So the good thing is that I think most governments in the world are aware of this problem, and they're pumping a lot of funding into this area of, say, climate change to address these problems. But this is the problem with how scientists do science. Okay, we must change. Let me tell you, we scientists work on discrete components of large problems. And we optimize those components. We know how to optimize them and how to solve problems related to just small components at the expense of everything else. That's why our planet needs help. When we talk about whole systems, if you develop sustainable society, you need to think about invent a new material. And I'm the entire ecosystem of the whole device, as well as how the whole system fits in the greater ecosystem. So we as scientists study components to studying those components and the whole system and how that system fits in the ecology of our planet. A challenge for us researchers in academia. And the future It's really in studying these systems. Okay, so what we've been doing in my group for the last 30 years is that in the mid-1990s, we discovered a whole new class of materials where one can combine inorganic units with organic units through strong bonds to make extended structures that are robust. We call it retention chemistry, meaning to build structures from molecular building blocks through strong bonds to make extended structures that have space, illustrated here in the yellow ball, space within which one can trap CO2 from air, one can trap water from air, one can store hydrogen and other things. One can control matter further. And not only that, it's not just one material that we discovered, but we've discovered ways of modifying the linkers, the size, their length, their functionality, and their connectivity. We have discovered ways of varying the metals in the multi-metallic units that are here illustrated in blue. The type of metal, the connectivity of those metals are all controllable, and we can also control the size of the pores, the geometry, and the chemistry of the pores, as well as the fact that it looks like we have uncovered one of the largest class of materials ever made by humanity. The possibilities are truly endless, because not only can you use these organic units, but you can use whatever chemistry has offered us for the last 100 years as building units to make these materials. The great thing about these materials is that they are confined. And that means that their behavior is consistent, their pore sizes are homogeneous, and they behave in a reproducible manner. The applications have been wide, not just in materials, what I mentioned before, but also biotechnology and medicine. So I think what's going to save the world is actually the periodic table, because for the last years, we have been stitching atoms together to make molecules, and that pharmaceuticals, polymers, molecules, and molecular chemistry, with the chemistry that we've invented, we can take those molecules and link them together to make new materials. And these materials encompass space within which one can do much more, such as trapping water from air, converting CO2 to so early on, some remember when we first discovered very stable, made them stable, and now we can actually dream materials for chemists, which are we call covalent organic frameworks. These have no metals in them. They're bonds, covalent bonds, to make extended structures that are also porous. You see, this structure is entirely made from carbon-carbon bonds and carbon-hydrogen double bonds, some of the strongest bonds. The future of carbon, because now what we can do is function the pores with the proper functionalities to trap CO2 and then cycle the CO2 in and out of the pores without the material breaking down, which is one of the weaknesses of the current carbon capture technologies. This material has been tested, and it is using water in acids, bases, and even corrosive and butyllithium. Okay, these are the same kind of bonds hold graphite together. They're extremely. We have CN bonds everywhere. One can functionalize them and fashion the pores for various applications. So, what is we okay? What billions of atoms, those each to an incoming, the surface area goes up from, say, 7,000 square per gram. And a gram of, and sometimes when I talk to judges, they say 1 gram of this covers a whole football field because it's and okay, so the reticular chemistry has been important now, demonstrated to have application in energy, in climate, in food, in water, in health. And I'm just listing here some of the things that people have been working on, like storage, conversion to fuels, like artificial photosynthesis, balanced electrons. All these things are being investigated, and some of them successfully offs metal organic and organic CO2 capture from air and flue gas. I'll show examples of that. Methane from air and methane storage for automotive fuel. It's an SOx capture. As food in a MOF and put it as a packet, packaging food and extend the shelf life of food. Same with vertical farming, green safe pesticide. I can discuss that if there are any questions later. But health, biomedical applications are, again, becoming extremely important for this materials, as well as water harvesting and desalination. So these are the molecules that are causing us a lot of problems. Some of the small molecules on our planet, and yet they are causing all these problems. They are part of the problem, but also part because we have invented. And I won't talk about how we've gotten from here to here, where now there is a Mercedes demonstration model that shows how a filled hydrogen could be used. The idea is to go from molecules to machines, or molecules to machines to society. This is an automobile filled with a MOF that we have designed, and it's a natural gas tank. That natural gas tank is the same as what you would get in any car, but it's filled with MOF. Because of the MOF, you can store 3 times the amount of natural gas, okay? And therefore, you can go 3 times the distance. All of this is being done in my lab. A chemist, and I'm going to get to this later, a chemist doing not just chemistry, but materials, as well as integrating the material to devices, and those devices going into machines that ultimately reach society. Carbon dioxide, we have designed, and I'll elaborate on this shortly, we have designed prototypes that take up CO2 from air and from flue gas. This results on our water harvesting device in the Death Valley. So the idea is that you have a MOF, and the MOF is designed to take, or on the molecular level, is designed to take up CO2 from air because we have covalently attached amines onto its internal walls, and the amines to take CO2 out of a stream to make clean air. I just want to say that there has been a big success in terms of blockbuster application of MOFs for CO2 capture, and that is from one of my colleagues at George Shimizu, one of the early investigators of MOF chemistry. His compound is shown here. It's a MOF, and it has pores. Into these pores, CO2 can slip in. CO2 from cement flue gas. Okay? Cement flue gas has up to 35% CO2. This material now over 450,000 cycles. Uptake is 2 to 4 million. Okay, blockbuster that's already being commercialized. BASF is scaling it to multi-ton quantities, and it's already deployed, and it's doing very, very well. So I congratulate my friend George Shimizu for this tremendous success. And that's just the beginning in terms of the use for CO2 capture. This is our material. We call MOF is based on a bed, packed bed, and we exposed it to air, okay, where CO2 is 0.1 millibar or about m. And you can see that it passes through the MOF, the CO2 goes down to less than 0.02 millibar. Okay, we're cleaning the air. Okay, this experiment works. The molecule is designed by us to be crystalline and functionalize precisely. Their pores fashioned for this purpose, as well as we can use this for gas uptake, which is but and here you have 20% humidity, and here you have 20 to 80% humidity. So CO2 competes for those sites very well in the presence of water. So here you go 15% off, it goes less than CO2. Okay, that is two examples of how less can be taking up CO2 from gas. And there are more examples that are coming online now. This, I think, is going to be the future of structure, and that is that are made from components. Okay, instead of having a polymer extended is crystalline, that are programmed to bind units. Heat it up, apply heat to remove the CO2 without wasting too much wood in the solutions. These they're cyclable, they stay in the device, and that they way assemble them and reassemble them. For MOFs, you do all that in water, and soon we'll be doing again water. So we have, in my preliminary result, that the scale-up of COFs could be done in water. The uptake from air is 0.3 millimole CO2 per gram. Not a whole lot, but it's cyclable. If I cycle this 100,000 cycles, material. And I think because the battery is made entirely of strong covalent bonds. Flue gas uptake is 1.9 millimole, and coal CO2 is 2. That's very, very good numbers. And that's just the first example of COFs in my lab to take up from air. So this is that we are applying our effort very strongly to address the CO2 problem. In terms of how air, I've talked a lot about this problem before, and I've shown you prototypes that we have designed based on MOFs. And I say as areas that are water been become worse, the UN projection. According to the 2040, we are going to 5 million people living in regions. Okay, and so if I make a MOF that works in the red region that can extract water from air in the red region, then I can also use that same MOF to extract water from air in where there's plenty of water, like the blue regions, but the water is not very clean. Okay, so all of this perhaps could get us to water from air anywhere in the world at any time of the year. Okay, so the result of this research, I've shown you prototypes that take up for each 100 grams of MOF. 100 grams of MOF can deliver 5 liters of water per day. Okay, and recently we figured out where the water molecules are. This compound is MOF-303. These are the pores, and the pores, if you're a molecule floating through the pores, you see pockets that are hydrophobic, hydrophilic, hydrophobic, hydrophilic, hydrophobic, decorating the entire region in terms of the pores. This MOF is made from aluminum. It's very inexpensive. And now I'm going to show you how the water molecules go in. So we're going to separate back. Oh dear. Okay. This is supposed to. Okay. Can you play the movie on slide? Oh. We'll get there. Right here. Oh. Oh. Okay. Almost there. Okay. So it's just, if you, there we go. Slide, you can see, which is the green is nitrogen and hydrogen. So hydrogen bond donor and acceptor. And now you bridge over the hydrophobic region through hydrogen bonds. So the first water molecules act as seeds onto which other water molecules bind. And we've located each water molecule by X-ray diffraction, by single crystal X-ray diffraction. So these are not computer models. These are actually data that is obtained from single crystal X-ray diffraction. So this MOF delivers 1 liter of water per kilogram of MOF per day. And this experiment was run in the Mojave Desert. This is a prototype that has a solar panel. Solar panel basically powers a fan that pushes air into the MOF. These are the students that. So based on those results, you can see how much we could deliver in some of the driest deserts in the world along the weather across the year, the months of the year. You see here, this is a productivity from 0 up to 100 liters of water per kilogram of MOF per day. And depending on the time of year you're in, your delivery amount changes, of course, depending on the humidity. But in all cases, you're delivering at least 10 liters of water per kilogram of MOF per day. And if you want 10 times that, then you use 10 kilograms. If you want 100 times that, you use 100 kilograms, and the 100 kilograms will stay there for 5-6 years. And at the end of that journey, you add strong acid to the MOF, separate it into its components, and reassemble it in water using cyclable condition, no discharge. So I'm just showing you the different productivity. It's truly an amazing MOF, and it's all result of many years of honing in our skill at designing MOFs and going in and crafting the interior so that they bind water too loosely, just right, to allow you to remove the water without heating to high temperature. Okay, the latest experiment is that these 3 heroes of mine, my students, went to the Death Valley, one of the driest deserts in the world, in Furnace Creek, the temperature 107 degrees, and they designed a briefcase-sized device. And you see the device here. It has pancakes of MOF that are stacked on top of each other. And during the night, they open this device to expose the MOF to the air. Water from air goes into the MOF, saturates the MOF. During the day, they close it, and they expose it to heat, and then they can harvest the water. Okay? So you see here a vial. Okay, this is Death Valley, okay? And the humidity is less than 10% when they were doing this. This demonstrates to you that you can create liquid drinking water, clean water in the desert. This, already we're scaling this, and as I said, I've shown you devices that deliver 5 liters of water per kilogram, per 100 grams of water per day. So this is a big success, and I think that we are realizing what I call, at least we're realizing the science that is going to lead us to a water independence to people everywhere in the world. Okay, so where is this all going? Okay, humanity has developed in the following way. We went from having small farms to mechanization of those farms and commercialization, to electrification, manufacturing, then to diversification and rapid production because of the computer age, and then we just sort of pass over the information age, okay? And we went from humans that are admiring their planet and love their planet to humans taking advantage of the planet. So something has to happen in order for us to live a sustainable life. And I think what's going to save us is the digitization age. I think that the next age is digitization. So I have basically turned my group into digital chemistry. And what I mean by that is that I shrink the whole into a box. There is no reason why my students can't do reticular chemistry in a box. A box is equipped with a robot that does the reactions, a detector that detects the outcome of those reactions, whether it's crystals or reactions or whatever properties. This could be an X-ray module or a GC module or some, let's say, also image recognition module. And then that information is fed into a machine learning program. Why can't we do that? I'm a synthetic chemist, okay? We can make devices now. So the question is that we need to change the way we think chemistry should be done. And quite honestly, chemists are minded scientists. Okay, we're very conservative. And I'm trying to break that. I'm trying to get out of the chemistry building and go to the computer science and say, I want to be a chemist in a computer science department, because that is a matter of survival for chemistry. And that's what I've been doing. So we have, in my lab, demonstrated that we can go from molecules to systems and to society. And I'm a chemist, a scientist. I think everybody can. And now we want to do digital reticular chemistry. So I have teamed up with one of the most amazing people I know, Professor Jennifer Shays at UC Berkeley. She's the Dean of the Computing, Data Science, and Society College. It's a new college that UC Berkeley has created. And we raised together plenty of money to create an institute that we call Baker Institute of Digital Materials for the Planet. BIDMAP, and BIDMAP is entirely dedicated to integrating reticular chemistry with data science. Students and her students work together, and this is there's nothing like States. So to do that, I also engaged with KFUPM and Aramco for a long time, and we're building a consortium for sustainable future so that we can, and we have this consortium of research where hard machine image recognition and visualization of research. So thank you for your hospitality and being here. Our research for your time. Okay.
Ladies and gentlemen, please allow me to invite Professor Wilson from the University of America to deliver.
On behalf of the leadership of the American Chemical Society, I'm pleased to join you in celebrating the opening of the 2022 Gulf Chemistry Association International Conference and Exhibition. I really appreciate the opportunity, and I very much appreciated the talk that was just given by Professor Omar Yaghi. I myself do a lot of work in CO2, and I really appreciate all that he's done, and it's so spectacular to be part of a important focus. I extend greetings to all of you from the global membership of AGS of over 161 members, with a special acknowledgement of His Excellency, Dr. Mohammed bin Mubarak bin Derma. Thank you so much. I thank the Gulf Chemist Union and the Saudi Arabian International Chemical Science Chapter of the American Chemical Society for the invitation to speak at this conference. I'm truly honored. This is my first time to Bahrain, and I'm delighted to be here. I'm very pleased that there are attendees from around the globe who have come for this conference to share science and connect with one another. I very much look forward to hearing about the exciting science and innovation that will be presented. Today I was asked to talk about the American Chemical Society in the Middle East, and I will do this. But first, I want to address the chemical sciences much more broadly. My focus is upon the future of chemical enterprise, ensuring that we as a profession are well prepared to address the challenges of the present and the future. This entails a strong, diverse workforce, knowledge of emerging fields, greater support of the public, partnership to tackle science and technology challenges, and a vibrant chemical industry. Through the years, we have made significant gains in science technology as different ages, the Stone Ages, the Iron Ages, the Industrial Ages, and we many times called the Golden Ages, the Golden Age of chemistry, the Golden Age of science, all the way from the 8th century to a period starting in the 1950s and even in 2014. We have reached a new age of the chemical sciences, what I call the transformative age of chemistry, the time where we have been able to demonstrate globally the importance and impact of chemistry and how quickly we can react scientifically to a global pandemic. We have had amazing discoveries such as the molecular motors discovered by Sir Francis Stoddard, CRISPR gene editing methodologies by Jennifer and Daniel Charpentier, and directed evolution of enzymes by Francis Arnold, and recently bioorthogonal chemistry, in part by Carolyn Bertozzi, all Nobel Prize-winning discoveries. But all are discoveries that point towards greater control at the molecular level, where design is in our hands. Truly, we are only at the very start of the possibilities to which this amazing research will impact, from human health to possible new energy drivers. And on top of this, technology is emerging quickly, from AI machine learning, enabling data-driven approaches to aid faster discovery and insight, as we've already heard a little bit about this morning, to quantum computing, my area, whose potential is not yet realized, but will be paradigm shifting, not only in our field, but also in our world. With much of the world considering the United Nations Sustainable Development Goals, we need chemical scientists and engineers that we truly hold the future of the world in our hands, as it is our profession that is key to nearly every one of the sustainable goals: food, water, energy, climate, and human health, to name only several. Indeed, our natural resources are scarce, as demonstrated by the limited abundance of many chemical elements in the Earth's crust. Research and development is increasingly driven towards these considerations. And as we look forward to the future, we must continue to build and extend the life of our vital resources and industries. And here, the petroleum industry, which includes so many vital feedstocks, for which there is no simple substitutions, continues to have a very critical impact upon our lives as well as our economy. We need to communicate this reality while continuing to push the frontier of energy resources and storage. Indeed, we have grand challenges and opportunities ahead of us so that we may make the world a much better place. As I consider our future, another grand challenge is in meeting the chemical science workforce needs of the future. Many fields, often viewed as lucrative, such as business and computer science, attract some of our best students. Yet the chemical enterprise is at the very heart of what will impact humankind and the world. For the future, it is so vitally important that we engage all populations across countries, cultures, and genders to ensure that we will be able to address the tremendous challenges the world has that will be solved by the chemical sciences. At this meeting, I am delighted that you are recognizing the contributions of women to the chemical sciences, and I look forward to hearing the success stories that the Empowering Women in Science workshop later today. It is women scientists such as these who will inspire the next generation of female scientists, entrepreneurs, and business leaders. We need to identify even more ways to encourage both boys and girls, young men and young women, into careers in the chemical sciences and support them wholeheartedly. It is so vital for us to have an incredibly engaged, global, and diverse workforce to address the challenges ahead of us. There are remarkable role models of women in the chemical sciences, the recent Nobel laureates that I have already mentioned, but also historical figures such as Marie Curie, who won the Nobel Prize in both chemistry and physics and the only individual to do so. There have been incredible contributions in industry or impacting industry. Helen Free, a former ACS president, was the discoverer of diagnostic test strips for diabetes. And from my own university, Loretta Van Camp, who was a co-discoverer of cisplatin, one of the leading drugs in cancer therapy. However, the examples you highlight today provide real-world examples, current examples, women with whom students will be able to relate, know, and see. Our chemical industry, our chemical community is an international community, and one of the great benefits of ACS is that it provides a global community of over 161,000 members and 2,000 staff representing over 140 countries and staff in over 20 countries. There are over 2,200 members in the Middle East, over 30 technical chapters, divisions, hundreds of local sections and student chapters, including more than 30 international chapters and international student chapters, such as those in nearby Iraq, Israel, Jordan, Qatar, Saudi Arabia, and the UAE. Science and technology transcends borders and such. I would like to see our community grow so that we can have a stronger network between all of us, whether we are from industry, academia, government, or some other career sector, as we consider the daunting challenges of the future. In my 33 years as an ACS member, it is through this network that I have built international collaborations, identified intriguing problems that are far too difficult to solve alone, and truly been able to delve more deeply into societal challenges. As every opportunity that I had and so many chemists have had and chemical engineers have had throughout their careers have had some ties through these international scientific networks. As mentioned earlier in this talk, there have been amazing chemistry discoveries that have not yet been fully explored. We are at the forefront of a new evolution in technology, providing a changing landscape and perhaps even disruptive landscape for the chemical sciences. And we have grand challenges, including the UN Sustainability Development Goals ahead of us. As we look toward the future, I thank you for your past and your future innovations and discoveries, from fundamental science to the most compelling applications. I look forward to all that we can accomplish in this new age of chemistry, the transformative age of chemistry, to improve the world and humankind via the transforming power of chemistry. I encourage you to be a part of ACS. It is the largest scientific society. We really need to build community much further than we have. It is so important. So often, if we talk to world leaders, they point to organizations such as the IEEE with 440,000 members. We know there are so many more chemical scientists, and it would be wonderful for all of us to be a part of a single organization where we can really push forward in terms of the UN sustainability goals, be the voice of the importance of petroleum, and so much more that really our world leaders need to hear so much more about. Truly the transforming power of chemistry and the importance of solving the society's biggest challenges. To close, I appreciate your time this morning and very much look forward to my continued visit, and I wish you all the very best of success. Thank you.
Thank you, Professor Angela. And now, ladies and gentlemen, I'd like to open the floor. Professor Ghada and Director of for Excellence in Nano Engineering in the Engineering Medicine at UCSD, United States of America. Please welcome her to the stage.
السلام عليكم ورحمة الله وبركاته. صباح الخير. ببدأ أول بشكر معالي الوزير الدكتور محمد بن مبارك للجمعة هذه الطيبة. I also want to thank my colleagues that organized this conference, Mr. Al-Khwaitir, and the advisory committee, Mr. Ashamri. So thank you very much for the invitation and for this very special gathering of chemists from the Gulf. This part of the world is rich in petroleum, and petroleum fuels chemistry because of the petrochemical starting materials that, as a student in the lab back in the early 2000s, we were making things, and how do you make them from molecules, building blocks, and it all comes down to petrochemicals, where you get your starting and building blocks, like we heard today, Professor Omar Yaghi telling us about beautiful chemistries coming together. Those starting materials all come from petrochemicals. So when I say a new chemical order, I have this thought for our gathering today, something for us all to think about. And maybe the collective response is always the strongest response, right? Strength through unity. And I thought of this beautiful gathering of the different Gulf countries, Oman, Bahrain, Saudi, Kuwait, Qatar. And I thought, why isn't there there is a GCC, why is there not a Gulf Chemistry Coalition? This conference has a special place in my heart. It's the first one, but I envision this to be the first step towards unifying the chemical R&D and industry across the Gulf. We are really ripe for that. I want to mention that this part of the world is the most youthful region in the world. We're very lucky in that regard, and because of the resources provided by petroleum industries, well educated. So you have a young population that's very well educated, resources available, and to know that we are all mostly chemists and chemical engineers here, I would assume, and we are in a land where petrochemicals, are the toy box for every chemist. And that's why I call it a new world order, an order where the Gulf societies, chemical societies get together and have a unified council, if you will. R&D efforts are pulled together, and we work as a region. I think that would be a dream come true one day, so I'm going to say it out loud. Only change is guaranteed. Nothing stays the same. I think we all know that, and if you're from, for example, Saudi Arabia, you know Vision 2030 and how things have changed dramatically. And so that's the change I'd like to see in our chemistry community, is just like there's a GCC, a Gulf Council for political reasons, we have one for research and development and innovation. So what you see in front of you is the 4 most competitive economies in the world. And it comes out of the Global Competitiveness Index. So what does it take? What's a competitive economy? A competitive economy is one that provides opportunities and livelihood to its populations, its country. And you see here, it's been a while since I've seen this slide. Things have not changed since that I was checking. Switzerland is considered, hold on. There we go. Switzerland is considered one of the most competitive economies in the world. It's also one of the top 5 wealthiest countries in the world. And importantly, higher education is up there. Internet use, or access to data and information technology, is important. Public institutions, soundness of the banking system, that's important. Tax rates, etc., but not as important sometimes, you'll see. Life expectancy is very important. You have to be alive in order to produce. And capacity for innovation, which is what we are here to talk about today. I'd like to really hammer in for excellent higher education and also healthy populations. So we look at Singapore, same thing, excellent business incentives over here with the soundness of the banks and tax rates, but stellar higher education systems and public institutions. Germany, as the United States, doesn't have as good a tax rate and such. However, we have one of the best higher education systems in the world, especially when it comes to R&D and capacity for innovation, very high. And then Germany here, looking rather similar to the US in terms of the profile. So I don't want to actually go too much into this because I think I'm not timing myself, but I should have, 8 minutes, 10 minutes. I don't want to go over this too much. I want to talk about Qatar, for example. Qatar is actually the only Arab country, top 5 countries in the world. I think it's almost 100-fold at this point. A great effort, right? Excellent higher education system, good use of internet or access to internet, and capacity to innovate. Life expectancy needs a little push, but a competitive. It's considered a UAE as well, research output and we see a competitive outlook, competitive issue with expectancy and being healthy. Our population healthier, more health conscious. Tax rates, soundness of banks is great. And the higher education system does need reform, and it is undergoing good reforms. Remember, these are old numbers, by the way. This is about 6 years old. So things are very different. Israel spends probably the top or second top per capita spending on research and development, and you can really see it in the capacity to innovate and in research productivity. And Malaysia is a very competitive economy. And again, you don't need to have a one resource country in order to compete and have a prosperous economy. Now, I wanted to say that research is an economic act, and it does lead to knowledge-based economies. And it's really to impress this on everybody in the room. It takes financial backing in order to get these R&D systems going and on into the innovation phase. Investment of money. But it will money. Large per capita if countries, it is below that needs to be put toward development. Uh, 70% off in the 50s, and as the R&D spend. In our Gulf on development is not reflected in the per capita of the Gulf countries. And I dreamed that. Okay. So again, I want to have the numbers. This activity. That's the case. So these are the wealthiest countries, right? And this per GDP per capita. So you can see that are competitive. It's no, they do spend. And it shows productivity list of countries, scientific technical articles, and countries spend a higher percentage of GDP per capita with, you know, high productivity, research productivity, academic articles. I think as they say, repeat, repeat, repeat. Point again, looping. States, there's kind of two they call knowledge, and Professor Amalia, well, we happen to come from the state that has the most innovation. California is now this just came out this year. And the higher, specifically the university engine of the state of California. So it's the best. You might say, an MIT, and MIT, but look at the numbers of students these public institutions are graduating. What we're looking at, what I'm advocating is mass, higher education, for the, not for a select few. This is what makes California the economy in the world and in the U.S. It's excellent systems like the University of California. Again, it's the graduate. In our before World War II, it would be touristy with and which was a post Second World War. It's jobs in the biotech that they can build. So growing jobs and jobs are in the IT sector, again, directly related to academic institutions clustering there, changing the city. Military. Research and economic, wealthier economies, even develop because investment in art. The strong economy number one, because you can't produce high but the UC in R&D, and we invest here that area, we put money to other countries. Failing, okay. We are lucky. You get chemistry, those of chemistry, and so I hope that it is a new chemical order and with our gap that our resources financially and our to better our industry in education, R&D, and staying healthy. Thank you for hearing me today.
Thank you very much, Professor. يعطيك العافية. We will commence the recognition, and I would like to invite His Excellency Mr. Al-Fayhan, Under Secretary of Oil of the Kingdom of Bahrain, to the stage. Chair to recognize. We begin with our notable speakers. Professor Omar Yaghi. Professor Angela K. Wilson. Professor Ghada Al-Mtairi. And now we move on to our esteemed sponsors. Diamond sponsor, Saudi Aramco. Aramco. The Oil and Gas Holding Company, Bahrain. Keminon. Platinum sponsor, Yesref. And our gold sponsors, Nazek. Abdulatif Abul Jadayan and Sons Company. German. Saudi Multi. Satorp. Air Products. And last but not least, the American Chemical Society. Ladies and gentlemen, Mr. Youssef Al Marzouk will now present Mr. Ahmed Al Khwaita with a token of appreciation for his continuous support to the Gulf Chemistry Association, GCA. And to mark this occasion, Mr. Ahmed Al-Khwaitor will kindly present a humble token of appreciation to His Excellency Mr. Fayhan Al-Fayhani, Acting Undersecretary of the Minister of Oil, on behalf of our honorable patron, His Excellency Dr. Mohammed Mubarak bin Dana. Thank you, Your Excellencies. Thank you. Thank you very much. With this, ladies and gentlemen, we conclude the opening ceremony of the first Gulf Chemistry Association Conference and 2022. The conference sessions will begin after the break. In the meantime, His Excellency will now open the exhibition along with our notable dignitaries. We ask esteemed guests in the back to please remain seated to allow His Excellency to exit into the exhibition hall. Thank you.